After the great presentation of Stanisław, it's time to dive deeper into technicalities blockchain. Our next guest, Michal Zejda of Eternity, will focus a topic which is the center of how the blockchain operates, consensus algorithms. Ladies and gentlemen, Michal Zejda from Eternity.
Hi, hello. How everyone is doing? Yeah, let's talk about the consensus a little bit. I think after this presentation you will understand even better the previous demo. So in modern computer science, like believe it or not, consensus is still one of the hardest problems. So let me ask you a question. Who is a programmer here? Yeah, a lot. But who is distributed systems programmer? A little bit less, and I understand that because no one enjoys pain, and distributed systems are painful. So it is technical, it's a technical conference, but I have a plan to walk you through this topic so everyone understands it really well. And this is my plan. Yeah. Let me tell you a little bit how we run Eternity as a software project. Let's talk about consensus later to understand what it is and how it relates to blockchain scalability. And how was it done in Bitcoin? Because Bitcoin was a big breakthrough exactly in this area, in the area of consensus. And is it perfect? Can we improve it? We wanted to have it slightly different to deliver what we promise. And finally, to close the presentation and make you feel like really good and have the handle of the consensus landscape, I will show you a couple examples of another consensus algorithms. We will have Bitcoin, the one Eternity uses, and a whole family of another ones. So yeah. Oh, before we start, who am I? I'm a hands-on developer, I'm systems architect, I'm a team lead. I have more than 10 years of commercial Erlang experience. Lucky or not, building distributed systems with usually high reliability, high traffic, low latency requirements. So yeah, that's more of an unlucky. But even important, it's who's the team behind Eternity. We have combined 200 years Erlang experience, and it's a small team, so that's a bad sign. And but anyways, on daily basis, I have a pleasure to work with and learn from one of the best specialists in distributed systems area. So thank you, guys. So let me take you on this journey and explain you how Eternity works, how it's written. Eternity, one of the things we want to improve is the consensus algorithm. And you can hold me up here. Why we need to even improve it? We know that the platform is written from scratch. Why we didn't get it right from the very beginning? After all, I just told you we are a whole bunch of decent engineers, so just get it right. Well, this is about something I call continuous operations, because blockchain teams operate in very specific environment. This is environment of lack of previous experience, lack of knowledge, lack of many examples. It's orders of magnitude less deployments than web services or chat apps. So this is still very unusual setup. We still learn a lot. And so to increase our chances, we came up with this idea to have operational blockchain from the very beginning. It took us about 2 sprints to implement somewhat equivalent, naive equivalent of Bitcoin blockchain. And by the way, Erlang features helped a lot here. Isolation of components, rapid development style, rapid prototyping. It took us 2 weeks and we had this operational blockchain. Side effects are scaling the team better. It was easier to onboard new people so they can catch up earlier with the new stuff and help us out. And I intentionally used continuous operation term instead of Kaizen's continuous improvement because it was our changes not always improved things. But having operational blockchain let us reason about it. We had before, we had after, we could measure. So this process helped a lot. And yeah, one of the mechanisms we wanted to improve over time from this base version is consensus. What even is consensus? In distributed systems where nodes are distributed globally, there is delay, there is network delay. Consensus problems surfaced in the 70s when first networks got created. The great work comes from the really amazing computer science engineers like Leslie Lamport. He wrote one of the best consensus algorithms called Paxos. When we need it with parallel writes. We need it with network splits. We need it in a system that some nodes behave as they shouldn't, like malicious nodes. Another time when you could hear about consensus is this. About 10 years ago, this like tsunami of new products under the name of NoSQL databases. That was the wave that tried to rediscover databases, and it was all great until they hit consensus problems. So again, those distributed databases hit all of those issues. Broken network, malicious nodes. And in blockchains, like it's our daily routine. Malicious nodes, we have them for breakfast. Network splits is like dynamic network. It changes all the time. Parallel writes. In peer-to-peer deployment, each node is a master node. Each node can modify this global state. So we have like the worst case scenario to have parallel writes. How to deal with that? Let's take a look on this diagram. This is peer-to-peer network, heterogeneous, different nodes, like PCs, some computing rack, large computing rack, even a mobile client. And users of the system submit some transaction, 1, 2, 3, 4. But as you see, each of those nodes received that in different order. So it's not really useful. One node can even tell that some transactions are not valid. If you transfer assets, tokens from A to B and from B to C in another transaction, if you received them in reverse order, they may not be valid. B may not have funds if it doesn't get them from A. So it's essential to have it final, finality to this state. How to deal with that? Proof of work. This is the big breakthrough in Bitcoin. Proof of work is a hashing function. It's a function that takes whole block, and by block I mean this group of those transactions that are not final. It computes a value of this block. It has all the transactions, it has some meta information and random part. And if the value of this function meets certain conditions, we call it confirmed block. It's final. Finally, everyone can use it. It shouldn't change. So how it works? By the way, the process of computing this function is called mining. So we compute the value of the function. If it meets conditions, great. If not, we have to change the random part. We compute again and again. And finally, lucky miner has all the arguments. It's a confirmed block, and he can push the block throughout the network. Why I call him lucky miner? Because it's very rare to find this random part. And there is a reason that the happy guy here is next to the biggest node, because the biggest node has the most computing power and the most chances to find a solution and find the block. So his version of the truth becomes the version, the next state, the next block, and he has right to push it throughout the network. Right? And this is the new block. It extends the chain of blocks. All the data in blockchains is in this log-like structure, hence the name, blockchain. And it's so rare that the protocol is configured, tuned, to find blocks every 10 minutes. Right? So this is the big breakthrough. It's a game changer. Before Satoshi, no one knew how to deal with those constantly changing, this dynamic environment. How to make the whole globe of different nodes, different computers agree on something. And this classic Nakamoto consensus, it started a new family of consensus algorithms. And yeah, but is it perfect? Like, are there any disadvantages? Well, of course, this 10-minute confirmation time. This is why we had to wait for coffee, because guys tune it to 1 minute. It's still a lot. Do you imagine using any mobile app and wait like 1 minute for a confirmation? It doesn't really work. And every block is computationally heavy because we need to apply all those functions again and again and again. So a lot of energy goes into every block. That's kind of wasteful. And because blocks have limited size, the transaction throughput is limited because you can put so much transaction in that big block that gets emitted every 10 minutes. So for Bitcoin, it's like 2, 3, let's say 5 transactions a second, optimistically. So can we change it? Is there any alternative? Where there is a new hope. It comes from Cornell University researchers. It's called Bitcoin NG. It stands for Bitcoin Next Generation. And it tries to benefit from all the security guarantees Bitcoin gives us, thanks to proof of work, thanks to resistance, to Sybil attacks, number of attacks. But it wants to increase latency. It achieves that by introducing 2 kinds of blocks. One key block that uses proof of work, this function, to elect temporary leader, and second one is microblock that holds transaction. And the leader is allowed to dispatch transaction and confirm them without proof of work. He only signs them. So this is very lightweight operation comparing to proof of work. The other way to think about it, to understand it like quicker, is to name things slightly different in classic Bitcoin algorithm. If you call a miner a leader, he will confirm events from the past. So when a miner finds this block, he mines a block, he's a leader of the events that happened in the past. And we reverse this approach. We choose a leader and he will confirm events in the future. Thanks to that, the latency is much smaller. Thanks to that, he will confirm events immediately and make the state the same for everyone. And this is how it works. We have the same transactions in the red, unconfirmed, on the like here. No, it doesn't work. You probably noticed that the list it's much shorter. It doesn't have full 4 events. It's because the leader that got elected by proof of work emits right away those tiny microblocks, and they can reach a network almost as he received them. So there is no need to accumulate this gigantic block and hash it. We can dispatch them and confirm right away. And there is like no accident. I put the happy guy next to big computing rack, because Bitcoin NG inherits security guarantees after Bitcoin. So again, the more computing power you have, the biggest chances to become a leader you have. So that has consequences. For example, new chain format. This is a key block that holds an ID of a leader. The ID is a public key. This public key tells you not only who's the leader, but also make you know if microblocks holding transactions are the real ones, not fake ones, not dispatched by malicious actors. So they are signed with private key corresponding to the public key in a key block. And yeah, we have difficulty. So this amount of work needed to provide proof of work is in key blocks, and microblocks are just chained. They are weightless from the protocol standpoint. We have leader, we have new leader, but you may ask, what's the incentive for the new leader to follow whole chain? Why he's not mining like a couple blocks before, or maybe on the top of the key block? This is done with a really cool crypto economic incentive, which is split fees. The leaders are rewarded for their work with regular coin-based transaction, but they also get transaction fees. If the new leader gets 60% of transaction from the previous generation, he's incentivized to grab as much as possible. So he tries to follow the most recent microblock. He doesn't want to skip anything because he would lose money. Anything he's not following, he will resign and get only 40% instead of 60%. So this is the mechanism that provides this liveness to the chain. But we want, there is still network propagation time. Basically every generation there may happen microfork because the new leader will not get soon enough the last microfork. And this is fine. This is just fine because signing operation is so cheap. The new leader will resign the same transactions and broadcast them to the system. Nothing is lost. And actually, it's very probable that his first block is very similar to the one he skipped, because the mempool is it's the same for everyone roughly in the network. So he will the difference, the transactions that are different will be the delta will be tiny. And let's talk about numbers. We want to dispatch microblocks every 3 seconds. So this is amount of time you're gonna wait for coffee. And we want to tune the protocol to elect new leaders every 3 minutes. So just like in Bitcoin, to buy a car or something, you probably want to wait more confirmations, more blocks, because it's probabilistic. And the more time you wait, the probability that the main chain switches to a fork is lower. So same here, same guarantees apply. So let's recap. What are the benefits? Transaction confirmation time, the coffee time, in a matter of seconds. Proof of work to elect the leader, hence the guarantees. And increased transaction throughput. This is interesting because we can dispatch more microblocks. They are obviously smaller, The original paper recommends 10 kilobytes blocks, but there is room for improvement. We want to tune our synchronization layer and use only transaction hashes. We will see how it works. So we'll make some experiments. But then it even gives us yet another, it improves the coefficient of transactions per second. So out of the box, it should roughly work around 100 transactions a second. And then we try to improve from over there. Yeah, so far so good. It works in our testnet. We are fairly happy with that. And so let's recap what I told you. I told you how Bitcoin consensus works, how this Bitcoin NG that we apply, that we want to improve the system with works. But what are another options? Important thing to remember when we look at another options is that consensus is core of your platform. It basically, even if you treat a platform as a product, it can change the characteristic of the product. If we, for example, choose proof of authority, which is represented by one private host belonging to private company, well, the blockchain is not independent. It's basically, it depends on some capital, some company that can shape the state of the chain. So it's important to realize how your architecture choices influence the product you want to build. So what is there? Paxos, Raft. This is this original family of algorithms from Leslie Lamport from 70s, 80s, 90s. It's not usable for blockchains, mainly due to a dynamic and untrusted nature of blockchain systems. And yeah, the communication overhead is pretty big, and they are super complex to implement. So it would be a danger that attack vectors would be easier to find. Those implementation may not be perfect. There is proof of work. We are one of the very few blockchains that still invest and like proof of work. But there are many, many shades of that. Some are CPU intensive, some are memory intensive. We use cuckoo cycle, which is memory intensive. There is proof of stake. That's a big competition. Exactly, as I said, it's different. Because here, about consensus, decide entities that hold the most tokens. And yeah, it may have some technical difficulties like nothing at stake problem. But first, it's your choice. What you want to build. Is it like open, public, trustless platform? Can it be with another consensus if large group of token holders can influence the consensus? Practical Byzantine fault tolerance, PBFT and Byzantine family, like Federated Byzantine Agreement. It's another kind of algorithm. It's named differently, but it has special nodes in the system, like witnesses or validators, and users can choose to listen those nodes or not, and those nodes provide confirmations. Even there can be quorum of validators, and they can use classic consensus algorithm to resolve conflicts between those nodes. So that's pretty cool. You choose the smaller group and apply classic algorithms to resolve any conflicts in that smaller group. There is delegated proof of stake. It sounds similar to proof of stake, but it's completely different. It's basically implementation of democracy on a blockchain, when you can trust your tokens, not tokens, but the power, voting power of your tokens to some another entity that can make choices for you. If these are wrong choices, you can take the support right away. Yeah, this is a number of pretty common now algorithms. applied, and the rest is these are new kits on the block or algorithms deployed to private environments, like proof of authority, proof of reputation, where nodes gain reputation and hence are trusted by another users to have good consensus, and another users agree with this consensus provided by them. Proof of elapsed time. This is interesting. Like, whole idea of proof of work is to deliver this delay in untrusted environment, and it's done by computation. And if in private environment, when everything is trusted, you can just put sleep, random sleep, and when some nodes wakes up, he becomes a leader, decides on consensus, and you are done. So running blockchains in private cloud, in private environment, is much simpler. And the last one, the DAG, Tangle, Spectre, Lattice, voting, blockless, this is completely new approach that breaks with the chain paradigm. It is no longer log-like structure, it's something else. Very likely it's a directed acyclic graph that lets have more parents for each block. Or it's a lattice, which basically maintains a chain for each user. So an event in a system requires modification of sender chain and recipient chain. We have also voting algorithms. We have blockless algorithms. So yeah, you can compose it out of pure transactions, not necessarily batch them in blocks. But yeah, it's all about choices. About choices, what you want to build, what guarantees you want to provide to your users, and make it stable. So thank you. I hope you have a better view on what's laying in the core of many blockchains and how it all works. Any questions?
Hi. So my question would be, which consensus algorithm do you think that Eternity would be using 5 years from now? And even if it's difficult to anticipate, at least probably the families of the languages. So when you mention the acyclical graphs, that is one family. The Byzantine family, it's another family. Maybe at least there could be one perception?
Yeah, thanks for the question. First of all, it's worth to mention that Bitcoin NG is a very good base to start with. If, for example, miners will find a way to play it, to attack, we can apply another algorithm on the top of that. For example, quorum of leaders. Difficulties with is another round of consensus. So first of all, we can improve. What we use 5 years from now? This Bitcoin NG is a pretty good choice for the future. It scales. And here we need to distinguish on-chain scalability from the off-chain scalability. Because Eternity implements state channels, it relaxes our requirements for on-chain scalability. Because real-time requirements are provided by state channels. It's like point-to-point, super fast off-chain communication. So those milliseconds of consensus, real-time communication will be isolated to state channels, and this couple seconds of consensus is just fine for on-chain solution. I'm full of hope for Bitcoin NG, but it doesn't mean we won't improve the whole system. Maybe we'll introduce sharding and simply scale it by leaving the same consensus, but managing smaller shards of the system. So we have possibilities. We want to be on the top to to deliver the best, the smallest latency, the best user experience. All right, thank you for having me. It was great to talk to you and explain you some of the dark corners of blockchains.